Perfect.
Well, I would first have to say thank you to the UK Catalysis Hub for everything that it's done for my career, and this is an amazing meeting, so it's great to see such a good turnout. My starting slide is a picture that we did from our book launch this year, so I don't get any money from it, but I probably should plug it because it's a very good book. So I think the computational kind of view in the Catalysis Hub is that we should try to bridge these often disparate communities. So the communities look at heterogeneous, homogeneous, biocatalysis, and we can use computational chemistry as a bridge. So I've also constructed this talk in this way. So I'm going to really kind of move away from what I've talked about before at these meetings, the CO2 utilization, and look at methane as another important global warming gas. I'm going to talk a little bit about how we can learn from biology and homogeneous catalysis to make better heterogeneous catalysis from methane to methanol. And if I've got time in the end, probably using this clock, I will talk a little bit about main group chemistry, some exciting work that's coming out. So a little bit of background. I don't think I need to go into too much detail in this kind of audience. So methane has a global warming potential that's about 30 times higher than CO2. So if you just look at forcing, you see a small change in methane is going to have a big impact on our budget for CO2 emission. However, that's not the only thing to consider. We also have to consider selectivity. When we look at selectivity over the long run, then CO2 is definitely the driver of climate change. CO2 lasts in the atmosphere about an order of magnitude more than methane. However, if we look at over a 10 to 20 year period, we see that actually in 10 years, methane actually does more for global warming than CO2, and then we progressively see less and less impacts. The other thing about CO2 is that it's very localized for a gas. So we can see, if I can use this pointer, I don't know if that works. Okay, so if we see this bar chart on the left, then we have localized sources. The wetlands and agriculture are big kind of contributors. So when we say wetlands and agriculture, this is some overlap. So we're talking about paddy fields, obviously cows and methane production, but actually probably the most accessible of the sources is our energy use. So that's oil, gas, and coal. Also, there's a lot of people are thinking about using kind of waste, looking at kind of natural methane production to use for energy. And if we see what we do with it now, so we burn about 140 billion cubic meters of methane every year. So we do this because obviously you have a less environmental impact over the short term, but when you burn it, what you're doing is you're producing CO2, which over the long run has a very big carbon footprint. The other thing we can look into compare CO2 utilization versus methane is with CO2, we're really looking to kind of reduce that overpotential, that activation barrier. With methane, you don't need any catalyst to oxidize it. What you need is a catalyst to selectively oxidize it to form useful products. If we can do that, then we can form an economic reason to not flare the stuff, but to use it for, say, fuels, for chemicals, for materials. So what we kind of try to do is take our cue from nature. So there's lots of biosynthetic routes to make natural fuels. So we can do this in two main ways. We have different oxidase enzymes, particularly the heme and non-heme oxidase enzymes, and they can go through either this decarboxylation routes or through a hydrogen abstraction and then form an alcohol. But either way, you can use that as starting points to form olefins and fuels. So when we look at kind of taking the enzyme and bioengineering it, now we can do a lot of alkane synthesis, so we can take even ethane to ethanol, but the one thing we can't do is methane. So that doesn't work in the P450s. So up till now, we've not been able to effectively bioengineer P450s to do this reaction. However, there are a number of homogeneous biomimetics that do this. And so what we tend to do with the biomimetics is we change the axial group, axial to the oxo, to form a more strong basic oxidizing agent to the hydrogen atom abstraction. So what actually changes chemically? Is there a physical reason for this? So if we do the calculations and we have a model heme, and so instead of having a cysteine in the axial position, we have SH, and we compare that to the biomimetics that are the most effective. What we see is we have a very, very big decrease in the activation energy for the rate-limiting step, which in this case is a hydrogen atom abstraction. So we go from about 25 kilocalories per mole all the way down to about 16. So can we explain this? Well, we have a very big difference in what we do with this electron. So when we move a beta electron from with the hydrogen, so it's an electron and proton transfer, and we have a look at the natural system, then we have this very clear A2U orbital that kind of goes around the heme. And this is what we're putting the electron into when we're doing this. However, the beta electron in our second system is also pairing up with a radical, but this radical now is in the axial ligand position. It's this nitrogen linker position. And so we can kind of rationalize that if we think of a valence bond approach. So what we do is we take the ground state's electron wave function for the reactants, and we kind of connect that as a wave function that's excited state in the product geometry, and do the inverse. And we look to see what happens at this conical intersection. And when we look at that, we say, okay, so there's an electron excitation that's going on, there's some bond formation, but a big difference is, in this case, is in this rearrangement of the metal and oxo in the actual oxidants. So this is what changes between the two. And if we break it down further and look at the thermodynamics, then what we see is actually the big change is here. So this is, again, this is the iron oxo electron affinity, as it were. And we can calculate that. So we can first find what is the proton affinity. So in this case, with both catalysts, there's a bit of a difference, but it's pointing towards the natural system. And when we look for the electron affinity, we also see that the natural system has a higher electron affinity. But then when we look at the basicity here, we see that actually the homogeneous catalyst is a lot more basic. So this is really what drives the lower barrier. And we see this with pretty much all oxidants for the hydrogen atom abstraction, is that it's actually this basicity. So we've done some work with colleagues in Manchester, where they actually introduced non-native amino acid species into oxidase enzymes. So this particular example is a CCP, so cysteine proteinase. So in this case, you don't have a cysteine in the axial ligand position, you have a histidine. But you have a similar kind of thing. You go, in this case, they calculate two turnover frequencies. They have the one that goes from compound 1 to compound 2. So this is basically an electron transfer. And you see when they do a substitution in the second coordination sphere, going from tryptophan to a sulfonated tryptophan, and they basically disrupt that proton binding network of the waters in the active pocket, you first see a slight decrease in the turnover frequency. However, what you see is then when you go from compound 2 to the protonated species, you see that K3 is dramatically increased. So what you've done is you've dramatically increased the oxidative power by playing with the basicity, by just disrupting that water network that you've got there. So a little bit on the calcs. And then what we can do again is we can look at that thermodynamics. So how is that thermodynamics driving this? And again, if you have a look at the delta GH on the left, you see with the mutants, you've got a much increase there. So that's, again, it's this increase in basicity that's really driving this reaction. So we had a PhD student that is just finished, actually. He's just doing his revisions now. And he decided, okay, can we kind of take what we've learned from the natural systems and the biomimetics, can we then use that to screen the zeolites? So this is kind of a little scheme of what we're looking at. So we're going to take our zeolite and we're going to exchange one of these bronzic acid site protons for a metal. So it's a metal exchange system. We're again going to see, can we do activation of oxygen to form a superoxo? Can we use this superoxo to form one methanol, and can we use then the metal oxo to form another? This was kind of based on some work that we did with Professor Graham Hutchins' group. So I was looking up to calculations in the system that didn't work, which is this system here, with the isolated metal centers. And in this case, what you find is that, oh, we do have a very, very high barrier for using the oxo to do the hydrogen atom abstraction. However, if we could form the metal oxo, we've actually got an accessible barrier that we could do some work with. So this made us think, is this a way of kind of screening zeolites for different metal exchanges? And can we use that to see if we can create active catalysts for methane to methanol? And so again, if we look at the valence bond approach, the takeaway is that really it's this metal center that needs to change. So we can actually use this as a screen, look at that basis, see what happens when we change that metal center. So we've done, here's a bunch of different metal exchanges that we've done. This is not extensive, but one thing that we have noticed is there's a few that are known to actually be very powerful oxidants. They're actually quite competitive with the best biological system and the best biomimetic homogeneous catalyst. So if we look here at the copper exchange, the sodium exchange, and the zinc exchange, we see that actually we're getting close. So I think I've got 10 minutes. Okay, so just quickly, I want to say a little bit of work that we've just finished with a group at UCL. So with Professor Tang's group, I think he'll be speaking in tomorrow's session. And we're going to look at polymers for photoactive. In this case, it's methane to ethanol. So we're forming the C2s. And what we're going to really look at is this covalent framework, the one left. We're going to compare this to titanium oxide and to graphitic carbon nitride, which is a standard kind of powerful photocatalyst for these type of reactions. I think I'm getting some pickups, so I'm going to move a little bit. Okay, so when we look at comparing the covalent framework to graphitic carbon nitride, we see that we've both got very good separation between the conduction and the valence bands. This is good for separating our electron hole pairs and doing some work. We see when we look at the reactivity, though, there's a very big difference. So when we look at titanium dioxide, actually, this is not a very good catalyst. We form mostly CO2, which if you saw from the first picture, we could probably do that just by lighting the stuff on fire. We don't need a catalyst to do that. If we look at the graphitic carbon nitride, we do actually start to form a lot of C1s and C2s, but in this case, the preference is more towards the methanol than it is for the C2 products. And then if we look at this covalent framework, we're actually getting increased turnover as well as increased selectivity to C2s, which was quite exciting. But can we explain this from a computational perspective? So from a computational perspective, we can see the first thing that's very evident is that we need water. So the spectra shows us there's a lot of water there, a lot of dissociated water with this particular catalyst, photocatalyst. And actually the water is very, very important to lower this barrier. If you look from dissociated water to this barrier for methane activation, we need that there or we will not activate this methane. And then when we compare what happens with the graphitic carbon nitride through to the covalent framework material, CTF1, we see that we have a lower barrier because we've got a slightly higher barrier for the water dissociation for this, this methane activation, which explains why we have a higher turnover frequency when we look at our covalent framework material from our standard graphitic carbon nitride. But then can we explain selectivity? Well, we think we can. So if you look in the case of the covalent framework material, our two most exothermic absorption sites are very close together. So we have an absorption site of the linker nitrogens, and we have an absorption site on the benzene. And that means that we've got a very good options there for them forming ethane. Whereas this is not the case when we look at the graphitic carbon nitride. Only in this case, the linker nitrogens are strongly exothermic absorption. If we look at, sorry, only the terminal nitrogens. If we look at the linker nitrogens, it's quite endothermic. Okay, so now can we explain then how we form methanol selectively with our graphitic carbon nitride? Well, in fact, we go through quite a strange mechanism where we first form this CH2OH, and then we regenerate the catalyst by abstracting the linker hydrogen. However, it's unsurprisingly for us, and actually this is kind of seen by a lot of the kinetic studies that the experimentalists do, when we're looking at going to ethanol, we go via ethane intermediates, which is not obvious, but is very interesting, and there's been a lot of labeling studies that actually shows the case. So I think that's all I wanted to say. I hope I've given you kind of an overview of some of the topics that we've covered, and thank you very much for listening.
Thanks, Matthew. We have time for some questions. Just to get them thinking, can you say something more about how you formed the methanol? Not the methanol, the ethanol. Because I was sitting thinking, I haven't read your paper.
Okay, so
I should go away and do that, obviously, afterwards. But
okay,
I'm just thinking, why? Because with the gold ZSM5 system, we make acetic acid.
Yeah.
And one of the key questions I've been keep asking myself is, why don't we make ethanol? It should logically make ethanol, not acetic acid. So what's different about your system here?
I have done a lot of, I find that mostly I think it's what is in that pool of partially oxidized hydrocarbons. So in this case, we've got, because of the thermodynamics, we've got a lot of methyl radicals on the surface. So in that case, what in biology you call recombination is, but it's not always the case. It really depends on what's on that surface.
Right. Okay, so it's more radical driven. You've had time to think. I get to have another go. Someone asking a question?
Hopefully I've explained it so well.
With the P45, you tried to engineer the P45, obviously in silico, to do this. But the real problem, I think, with P45s is the active site. The methane is just too small to do this. So you'd actually have to engineer the heme part of it, I think. Is that what you were doing?
So I've got to say, it's not what I've been doing, it's what our colleagues have been doing, because I'm a computational. So indeed, there is a big kind of, so hemes have a few different ways of kind of directing the catalyst. One is that they've got type binding of the substrate. The other is that you exclude or include water molecules. That's reported, some understood if people don't work on it, maybe, but it's a very, very strong. So what they've really been focusing on is both second and first coordination sphere. So the first thing that they started with was changing with different Hammett parameters, changing this either the histine in the CCPs. But that didn't do much, so that's why I didn't talk about that. Actually, it was a second coordination sphere changes where we disrupted the water that actually had the big effect on basicity. So instead of actually the first coordination sphere of the heme, it's actually slightly further away from it.
Yeah, it's fascinating.
Yeah, nature's always wonderful.
Oh yeah, but did they? I mean, there's another related set of enzymes. It looks like we're having a conversation here. I think we should just go to the bar and have a conversation.
Yeah, we can later.
Oh, does anybody, please, Santosh? I'll ask you the other question in the bar.
The bar, yeah.
Thanks, Mark. Very nice, very nice talk. I'm wondering about the ZSM5 system. Which metal element did you try?
So we tried a lot of the transition metals. We stuck to transitional metals that were redox active mostly. I know that you've seen zinc in there as well, which is not so redox active. So we did choose a few that were kind of formal oxidation states +2 or whatever, but mostly we looked at the very redox active middle of the table transition metals, because those ones are the ones that you're going to have quite strong oxidative power.
Did you try copper and iron?
Copper's good, iron's good. Yeah.
But, did he try any, I mean, PhD student, did he try any experimental work of that?
No, he was purely computational. It would have been lovely if he could have had some of your expertise on zeolites for a co-supervisor. But no, it was purely computational. So this, at the moment, it was screening. Something for the future, for sure.
Thank you very much for your talk. I have a question about the importance of methane activation process. I feel that if you can stop the movement of the methane molecules by doing some way, you may have enhanced conversions or reactions of methane. Also, for example, if you introduce the hydrophilic circumstance around the active site, what kind of things can you expect? Can you do the theoretical calculations for speculating this phenomenon?
So I'm going to take the harder one, which I think is the first bit first. I really think this is very interesting to kind of look at mass transport effects, particularly in the zeolite system. So in the zeolite system, I think that the first screening will have to be kind of on the activity of the active oxidants. But after that, I think this kind of the mobility and ability to absorb methane and ethane is definitely something that has to be screened as well. So we can do that with kind of MD stuff. When it comes to looking at the oxidant in the enzyme and the effect of water, this is something that we can do computationally, and we have done. So what we usually do in the QMM methodology is we first do a mutation, we allow the enzyme to change structure, and then we solvate it over many, many cycles to see what kind of solvation we get in the active site. So depending on how you change this tertiary structure, you will change the amount of hydrophilicity in our active site, so we can model this.
Okay. Also, I think the quick removal of methanol is also important factors, right?
Definitely.
But biosystem can do this, but in a heterogeneous system, I believe it's very hard to do. But do you have any idea about it?
So again, this is something that's going to be incredibly important for the zeolite system. I think when you look at, particularly when we're looking at ZSM5, and you look at methanol as actually being important in protonated ZSM5 as a starting point for forming a hydrocarbon pool, then actually you may find out that you get other reactions towards C2, C3s, and towards olefins that you'll see inside that zeolites. So I think that's something that has to be modeled as well.
Question online.
Oh.
Yes, this is from Santosh Kumar. It says, no, another Santosh. Yes. Is your photocatalytic reactor set to as a static in flow or static?
It was a flow reactor system. I don't know 100%. I'm not the expert to tell you this, but it was under flow conditions.
Yes. Okay. He was just wondering what makes them stable in this condition.
So we had a lot of questions about stability, for the catalyst stability in particular. In fact, for this particular journal, we had to, well, I say we, not me, my collaborators had to do time online for a long, long time for this covalent framework. They don't see any degradation of, and they know that the carbons come from the methane because they have done labeling experiments for that as well. So it's definitely stable. Why it's stable, I'm not 100. I bow to more experts, but it definitely is.
Okay. Thank you.
Okay, thank you very much.